So this is a video about topic 4 of Edexcel GCSE Physics P2, which is all about momentum, energy, work and power. You know that normally I do my little assessment videos first that go through how to get certain grades, but on this topic area, because it's quite a short condensed topic area, there's not much points for me going through that. What I'll say though is there's a lot of sort of factual knowledge in terms of like stopping distance in here to begin with, and make sure you understand that this is an equation over here. So total stopping distance equals thinking distance plus braking distance. That is not given to you. Please make sure that you remember that one. That is one of the equations that is not given to you. Also, this idea over here, let's quickly highlight it beforehand so I remember. The idea over here about the conservation of momentum, okay, and this calculation that I do down here about calculating the velocity of the van afterwards, that's going to be key. That's like an AA star calculation. That's right at the top end of things. Try to do that. It's a difficult calculation, but it's normally worth somewhere in the region of 6 marks. So it will come up as a 6-mark question at the end. And there's a few tricky things I like to ask about work done, kinetic energy and gravitational potential energy, but they're pretty straightforward ideas. I also go through how to rearrange an equation without using triangles here. So if you're happy using triangles, then use the triangles. But if you want to try to do it without, then you can follow me here. Right, so let's get cracking. So starting from the top, braking distance and thinking distance. I like to go through thinking distance first because it's what happens naturally first. You think before you brake. Now remember, it's a distance travelled, so it's a distance, not a time, which is often confused. So don't think about a faster braking distance. It doesn't, or faster thinking distance. It doesn't work like that. It's a longer or a shorter thinking distance. They're the words we should be using. So thinking distance is a distance travelled while the driver is reacting. Depends upon the speed, not so much the mass. That is a mistake there. Let me put a line through that. Not so much the mass of the car, definitely the speed of the car. The driver's reaction time, what that's affected by, such as drinking, drugs, alcohol, tiredness, or distractions. The braking distance, that does depend on the mass, the speed, the quality of the brakes and tyres, quality of the roads, the amount of friction between the tyres and road as well. The amount of friction that surface has while we're in this point of friction. Before I forget, that total stopping distance is equal to thinking distance plus braking distance. So the distance you travel while you're thinking about braking and the distance you actually travel while you're braking. So the amount of friction, well, we'll talk about friction over here in terms of between the tyres and the road. You can actually investigate that. It's a similar setup to the F equals NA experiment. The only main difference this time is that we're using smaller weights, so that, and there's spring balance in there to help with those smaller weights, to see what mass actually, or what force therefore actually causes the block to move, and therefore how much friction there is on that surface. Pretty straightforward, bog standard facts. Read through your pack on that and your revision guide on that, and you'll be fine. Right, momentum. First thing you need to know about momentum is a vector, as I mentioned before. Okay, so remember that means it's got magnitude and direction. If you want to know some more vectors, go back and watch my topic 3 video. So momentum is equal to the equation mass times velocity. So look at its units, it's kilogram meters per second. So if you're doing P3 in triple physics, this will come up again, momentum. And sometimes I like to ask why it has the units kilogram meters per second. And all you need to say is it's because it's mass, which is in kilograms, times by velocity, which is in meters per second. Okay. So whenever we're applying a force, that causes a change in momentum. So if you push an object, you're causing its momentum to change. If it was originally stationary, it has no momentum. Once it's moving, it will have momentum. So the momentum has changed because you've pushed it. So we can figure out what the force is by doing change in momentum over time. So this helps us understand collisions. So when you catch a cricket ball, you bring your hands in towards your body as you catch the ball. This makes the time for the ball to slow down longer. Okay, so it increases the time. So the change in momentum takes longer. Okay, so the force is therefore smaller. Remember, if the time is now bigger, the force is smaller. It just means when you catch the ball, it doesn't hurt as much, or it's less likely to pop out your hands. Cars and trains, use this idea as well. They have crumple zones at the front, like over here. So that increases the time for the collision, so that decreases the size of the force. Because remember that change in momentum is happening over a longer period of time. A good way of saying it is the rate of change of momentum, so in other words how quickly the momentum is changing, has decreased. Airbags do the same thing. They decrease the rate of change of momentum, okay, therefore decreasing the force. All that force is the rate of change of momentum. And if you ever hear that phrase rate, that just means divided by time. The rate of change of momentum is force, because it's changing momentum over time. Rate of change of energy, which is going to come up later on, is power, because it's energy over time. So here's this idea of the conservation of momentum. So whenever there's a collision or an explosion, momentum is conserved. So this could be a skateboarder standing on a skateboard, and then he pushes off the skateboard, he jumps off it, he goes forward, the skateboard goes backwards. This is because the momentum before must be equal to the momentum afterwards. So if he's standing on a skateboard, his momentum is 0. As he jumps off the skateboard goes backwards, he goes forward. The total momentum must still equal 0. One's negative because it goes backwards, one's positive because it goes forwards. Remember, this doesn't always apply. If there are external forces, the conservation of momentum does not apply. 9 times out of 10, in the exam question though, they don't touch that point. They focus on the conservation of momentum applying. So here's a calculation to help you out with that. So, what is the velocity of a van after the collision? So we've got the blue van, 500 kilograms, 5 meters per second. Yellow van, 400 kilograms, 2 meters per second. Blue van, 500 kilograms, we don't know the velocity. Yellow car, 400 kilograms, 4 meters per second. So let's figure out how much momentum each of these had. 500 times 5, 2,500. 400 times 2, 800. So that's 3,300 totally before the collision. That's where I've got to over here. Okay, that's generally worth about 2 to 3 marks. I know from the conservation of momentum, the momentum before must equal the momentum afterwards. So that means the momentum afterwards must be 3,300. So do I know the momentum of either of these? Well, the total momentum is 3,300. 4 times 400 is 1,600 or 1,600. So that's 1,600. The total is 3,300. So this one must be those two numbers take away from each other, which is what I've done over here. That gives me 1,700. That means this blue van has 1,700 kilogram meters per second of momentum. If I want to figure out its velocity from rearranging the equation for momentum, it's mass. It's a momentum divided by mass. I'll quickly go through the little rearrangement of that here with a triangle as well. So P equals mv, so momentum equals mass times velocity. If it's times on one side, it's divide on the other. So I want velocity, so I've got to get rid of the mass. It's times on this side, so it's divide on the other. Remember, if it's divide, it goes on the bottom. So momentum divided by mass equals velocity. Okay, if you want to do it as a triangle, let's get rid of this. Remember, the bits that times together end up at the bottom of the triangle. Okay, so if I have my triangle here, there we go. If it's on top, it's divide, remember. And these two at the bottom are times. Mass times velocity, they're at the bottom. Mass and velocity, momentum on top. So if I want my velocity, I cover it up. Just momentum divided by mass. So remember, if you try to get an equation to a triangle, the two things that times together, put at the bottom. So yeah, we end up with 3.4 meters per second. Difficult calculation, worth a lot of marks, so follow it through step by step. It's not one to try to skip, do it all on your calculator. Show your working, spread it out. 6-mark question, show you working step by step. You can potentially pick up 5 even if you get one part of it wrong. Right, work done. So work done is whenever a force is applied on an object over a distance. So any time there's a change in energy from having gravitational potential to kinetic or any other type of energy, we say work is being done. So if you think about a car and the brakes being hit on the car as it slows down to a stop, kinetic energy is lost. That kinetic energy is lost to the surroundings as heat and sound, so work has been done. Okay, the force of the brakes has been applied over that braking distance. So if a question says, how much kinetic energy did the car have when it was going at 30 miles an hour? So let's say it had 1 million joules. How much kinetic energy is it lost when it brakes and comes to a stop? It's 1 million joules. When it comes to a stop, it's got no kinetic energy. 1 million when it's going at 30 miles an hour, 0 when it stopped. 1 million joules of kinetic energy has been transferred, so that means 1 million joules of work has been done. Let's come towards the end of this one now. So kinetic energy is our next little topic here. Oops, I think Word's just got a break on me here. Apologies, I'll just get that Word document back up. So moving on to kinetic energy, it's a slightly tricky equation. There's a half in there, there's a squared in there. I'll show it to you right now. Thank you very much for remembering where I was, or remembering the document. Let's get down to it. Oops. It's too far. There we go. So there is a squared in it, there is a half in it, but don't worry about that. What the half actually means is that it's part of the equation. So when you have your numbers, it's just 0.5 times by the mass times by the velocity. Okay, so what you can do is you can just half the mass and then leave it at that. So if the mass of the object was 100, you can put the mass in as 50 and forget about the half. The other key thing is this velocity squared part. You've got to remember to square your velocity. Okay, so remember you can say that work done equals force times distance, but it's also equal to kinetic energy, so it's also equal to half mv squared. Alright. Power. Power is the rate of energy transferred. Okay, so in other words, it's the amount of energy transferred per second. In other words, the work done divided by time. Power is measured in watts. Okay, so power is a joule per second, which is also the definition of a watt. Gravitational potential energy is pretty straightforward. It depends upon three things: the mass of an object, the gravitational field strength, and the vertical height that you're moving it through. So if it loses gravitational, now this is the key point over here. As it loses gravitational potential energy, it's converted into object. It's converted into kinetic energy. So as an object is dropped, it loses gravitational potential, becomes kinetic. As it's raised, the kinetic energy becomes gravitational potential energy. This is the idea behind roller coasters. So you can combine those two equations. If you figure out the kinetic energy, you can make it equal to this and then figure out anything here. Or if you figure out the gravitational potential energy, you can figure out this side over here. This could potentially be a very, very hard question. And it leads to this equation over here. I've never seen it come up, but I've always left it in here because I think it could potentially come up as a very, very hard question. So, like a 6 marker at the end of the test. So it's half mv squared is equal to mgh, because mass is on both sides of this. Here's mass here, here's mass here. If you're moving the mass over, it's times on this side, divide on that side, so then masses cancel out. So you're left with this equation. Well, let's say we want to know how fast it's going to go, you need to rearrange for v. So it's times by half on this side. If you didn't know, the opposite of times by half is times by 2. Because imagine if you halved something and then you doubled it, it's cancelling out. So you put 2 on the other side, times by 2 on the other side. Because it's squaring, you'll do the opposite, so square root. So from that we can calculate how fast an object's going if it drops a certain height. And that's what I've done over here. You might want to look through that bit again, but remember that it has high gravitational potential energy over here, that becomes and a low kinetic. It goes the other way around over here. At the bottom, you can have no gravitational potential, but a maximum kinetic. And that finishes our video on topic 4.